All right, it's a great pleasure to have Eric Ling talk to us about the analog of the Schwarzschild solution in asymptotically cosmological spacetimes.
Okay, great. Thank you, Shadi. I am happy to be here and talk about this. This is some preliminary work that my girlfriend, Annachiara Piubello, and I have been working on. And so, you know, we don't quite have a paper yet, but we have some ideas. And I think part of this talk is also just to hear what other people's opinions and ideas might be from the mathematics that's going on here. Okay, so the analog of the Schwarzschild solution in asymptotically cosmological spacetimes. Okay, so let me give an outline of what I'm going to talk about. So the Schwarzschild spacetime. So first we'll quickly go over the Schwarzschild spacetime, and we'll talk about you know, its successes and its limitations. And then we'll do the same thing with cosmology. So in cosmology, we model the large-scale structure of the universe through the Robinson-Walker type spacetimes, and they do a good job at describing the isotropy of these spacetimes of the large-scale structure spacetime. Okay, and so then we'll discuss about how to possibly combine the Schwarzschild and cosmological models. And this isn't new, so people have been working on this before, but there was, mostly physicists working on it, and there was some debate over the implications of what these solutions are saying. And so, that's always hard, right? What do these solutions mean? So let's not ask the hard questions and just ask the easy questions and just do the mathematics of it, whether or not the math is hard. And then we'll discuss some results on geodesics and horizons that Anna and I found with these spacetimes. Okay, so, okay, but before I do that, there's a certain philosophical perspective that I have, which is that theoretical physics is really a mapping of mathematics into the physical world, right? If you want to describe some type of physics, right, what we do is we have some mathematics that's able to predict what we observe in experiments or observations. And it's important to understand, I believe, when this mapping fails. And an example of this, which is well known amongst all of us, is that orthodox quantum theory fails to describe point particles that are clearly observed, like on a detector screen. And so one could say maybe this isn't necessarily a failure of orthodox quantum theory, but it's not necessarily complete. It's not describing the full story of what we are observing, right? In particular, we are observing particles when they get detected on a screen. And so a question that I want to ask is, well, when does this mapping fail for general relativity? When do we have these limitations in the mathematical models that we have that describe the solar system or the large scale structure of the universe? Okay, and then, so lastly, general relativity, it describes the large scale structure of the universe, but this is done, when we talk about general relativity, we talk about doing observations from Earth, right? We look at the orbits of planets around the sun, we observe light from distant galaxies, right? So all of these observations are done through Earth. And so if we want to ask this question of when does this mapping fail for general relativity, we have to think about it in the lens of the observers on Earth. I mean, this is all we are, right? We're just humans on Earth that make observations. Okay, so let's talk about the Schwarzschild spacetime. And right now I'm just looking at the exterior part of Schwarzschild. So I'm not looking at the interior part or the black hole. So written here is the Schwarzschild metric. I'm choosing units where G and C are 1. The spacetime manifold is R times 2m times infinity times S2. And so the successes of the Schwarzschild solutions are that it describes Mercury's perihelion advance, it describes the bending of light and gravitational time dilation. So all 3 of these things have been observed, and the Schwarzschild solution does a good job at modeling all 3 of these. And so this is, one of the successes of general relativity. So this is good, right? This is what I'm trying to say. Okay, Now, the Schwarzschild solution is asymptotically Minkowski, and what I mean by this is that if you take R very large, then this factor, right? Oh, I actually have a pen here, so let me use my pen. This factor 1 minus 2m over R, right? When R is very large, that's going to be close to 1, and so then you get back something that looks like the Minkowski metric. And so this is where I want to say that the mapping of mathematics into the physical world is not really complete. Because in Minkowski spacetime, we know from our studies of Minkowski spacetime that has the Poincare isometry group, there really isn't a preferred reference frame in Minkowski spacetime. But observers on Earth, they very clearly do have a preferred reference frame. Pretty much all of the observers on Earth are traveling on the geodesic that the Earth is traveling on. And so I think maybe failure is a strong word to say of the Schwarzschild solution, but I do believe that this is a limitation of the Schwarzschild solution. And so I think in the abstract, I say in the abstract of this talk, I said, well, okay, the Schwarzschild solution is not static, or sorry, the Schwarzschild solution is static, but we know that the universe expands. And so that's a non-static solution. And so somehow one should reconcile this. But one can take an interesting perspective, which is that, let's say in about 100 billion years, the redshift of distant galaxies isn't going to be noticeable. So in 100 billion years, people won't be able to see galaxies from far away, but the local cluster of galaxies, they'll still have small collisions between galaxies, which will ignite stars, and those stars could create life. And so that life could be intelligent life, and then they would come up with their laws of science, but they wouldn't be able to detect the Hubble expansion because there wouldn't be light from distant galaxies that they can see. But this would still be a problem for them. I think if they ended up getting this Schwarzschild spacetime, they would see that it does a really good job at modeling the dynamics of their solar system that they have, but they should still recognize that there is a very clear preferred reference frame of whatever planet they're on, and then but their model, this Schwarzschild, which is asymptotically Minkowski, doesn't select out a preferred reference frame when you go out to infinity. And I think that this really is a problem. Okay, so now let me talk about cosmology. The class of cosmological spacetimes describing our universe as a whole are given by this spacetime manifold. M is 0 infinity times sigma, and the metric is minus dt squared times a or plus a squared of t times h. A is the scale factor, and it represents the expansion of the universe. And these are called FLRW solutions. They're named after Friedman-Lemaitre-Robertson-Walker, who first studied them. There are three different types of solutions corresponding to the different types of isotropic models that one can have. And I think it's an important question in cosmology to try and figure out, well, which one of these best models our universe, right? Our universe can't be modeled we know all three of them can't model the universe because there should just be one space-time that exists. And so one should figure out what is the best one. And I think a hint at trying to determine which one is the best one would be to look at their isometry groups, right? And so the K equals +1 FLRW spacetime, that corresponds to having the spatial slices being S3, with S3 having the round metric, and then its isometry group would just be O4, right? So the orthogonal group in 4 dimensions. So here I'm writing the isometry group there for the K equals 0 FLRW spacetimes. The isometry group would be just the Euclidean group, right? And this composed of the translations plus the orthogonal group in R3. And so this would just be the isometry group would be R3 and then semi-direct product O3, right? And then the isometry group for the K equals -1 FLRW solutions, this is the Lorentz group, right? And so I think, eventually one day someone should ask the question, which one of these spacetimes does the best job at modeling, our universe? And I think, one should take it from one should see which one of these isometry groups might actually provide some way of understanding that. And I mean, in particular, this one, 013, this is the Lorentz group, right? And so this is saying for these hyperbolic, the k equals -1 FLRW models, that you have Lorentz invariance, that the isometry group is the Lorentz group there. And so you know, these isometry groups, they're describing the isotropy of these FLRW models. And so they are basically saying why these FLRW models are isotropic, right? If we are living in a k equals +1 FLRW solution, then one could argue that, like, well, then that orthogonal group O4 should be fundamental. And so then you would say, okay, well, then the orthogonal group has to be a fundamental group of the universe, this symmetry. Now, I think personally that Lorentz invariance is fundamental. I don't believe Lorentz invariance is fundamental because it appears as the isometry group or as a subgroup of the isometry group in Minkowski spacetime. I believe that Lorentz invariance is fundamental because it's describing the isotropy of the k equals -1 FLRW solutions. And so if I had to pick one of these that would best describe, you know, the universe, I think if anyone knows me, I prefer the k equals -1 FLRW solutions. I think that their Lorentz invariance is somewhat fundamental. With that said, I'm actually just going to focus on the k equals 0 FLRW solutions in this talk because they're easier to work with. But you know, from a fundamental perspective, I think it's a good question to ask which one of these is best. And I think if you're going to ask that question, you have to look at their isometry groups. And I think the Lorentz group is a pretty good motivating reason to pick out the k equals -1 ones. Okay, so that was just my spiel about the isometry groups. So the FLRW spacetimes, they are solutions to the Einstein equations with a perfect fluid. So here I've written out the Einstein equations with a perfect fluid. When I write it like this, I'm assuming that the cosmological constant is absorbed into the stress energy tensor. And so it's part of the rho and p that make up the Einstein tensor. And so this system is right. If once you have rho and p, then the Einstein equations tell you what the scale factor A here, so that's the scale factor. Once you have rho and p, then the Einstein equations tell you what the scale factor should be. And so once you specify rho and p, then you close the system and you can find the scale factor. And so, you know, normally one says, oh, well, rho and p should satisfy maybe a radiation dominated era or a matter dominated era, and this specifies different forms of what rho and p should be. And from there, then you can calculate what the scale factor is. Okay, so that was cosmology. So the successes of these cosmological models, these FLRW solutions, is that, well, I mean, they inherently have the isotropy of the universe contained in them through the isometry groups that you saw. They describe Hubble expansion that we observe, right? We observe the redshift of hydrogen from distant galaxies, and so this goes well with having the universe being modeled by an expanding FLRW model. And then importantly, what I think is really important is that it selects out a preferred reference frame. So here, this U that appears in the perfect fluid is describing the direction in space-time of what these particles are traveling on. And so I think that this is important because it's really selecting out a preferred reference frame, right? So the integral curves of U are these curves right here. So these are the integral curves, right? So if I could draw, like, this might be, you know, your sigma, here is your P, right? And then an integral curve of this vector field would be something like this, right? And so these curves, they are time-like geodesics, and they describe the particles that make up the matter in the universe. This is like what, you know, when we're describing the universe as this perfect fluid, we're thinking of this is describing the stuff that the universe is made of. This is like the matter, things that make the matter, the dust, or the stars, the dust, and the galaxies. And so, you know, what I think is, you know, what this does that the Schwarzschild solution does not do is that this selects out the preferred reference frame that the Earth is on. The Earth is moving along the preferred reference frame that it travels, I think, is dictated by this force velocity of these FLRW solutions. And I mean, I'm not trying to say anything that deep here necessarily. I'm just, making an observation that, the Earth is made up of something like 10 to the 30 particles, right? And most of them are traveling along the same, their velocities are very similar to each other, right? Eventually, of course, we observe cosmic rays, right? Cosmic rays hit the Earth at like 99.9999% the speed of light, right? But those are one out of the 10 to the 30 particles that make up the Earth, right? And so those things weren't preferred. The preferred ones are really the ones that are traveling along some direction, and I think this direction is dictated by this U here. Okay.
Eric, can I ask a question? So why can't we say that, well, Schwarzschild also has a preferred frame because it's a static spacetime, and don't all the static spacetimes have a distinguished time-like direction?
Well, I mean, Minkowski spacetime is static, right?
What?
Minkowski spacetime is static.
No, but you were talking about Schwarzschild. So I agree that Minkowski doesn't have a preferred reference frame, but it seems to me that Schwarzschild has at least a preferred time-like direction.
Yeah, I guess once you get close enough to the black hole, and then you see, because of the static nature of that time-like vector field, then yes, I can see that maybe the preferred reference frame should be given by the one that is orthogonal to those slices, right? So
yeah,
so
I mean, that's
agree with.
And also in your case, you're referring to a preferred reference frame, but the vector field U or d by dt does not actually single out a frame. It only singles out a time-like direction. No, you still have the freedom of rotating the space.
Yeah, you're right. I guess I am just thinking out the time-like direction. You can still rotate around, and that I would still consider this a preferred.
I'm wondering if the preferred reference frame is the right way of saying what you want to say.
You're right. So maybe reference frame is not necessarily the right thing that I'm trying to say right now.
Yeah. So maybe you want to use a more descriptive terminology there, perhaps.
So maybe what I really am trying to say is that there's a time-like direction that
yes, I understand. Or there is another way of saying it is there's a preferred foliation in this case.
Yeah.
Which
okay.
is more than just a preferred time-like direction, but actually a foliation. Am I right that there is actually a preferred foliation here?
Yeah, I would say so. I mean, the isotropy implies this foliation that you get, and then the orthogonal, the orthogonal vector field to that is this U. Right.
See, so you could have a time-like Killing field that is not hypersurface orthogonal. Then it won't give you a foliation.
Yes.
Right. But in this case, I think it does, or in and also in the static space-times it does.
Yeah.
That's anyhow, that was just a comment.
It will do it in static spacetimes, and it will do it in these FLRW models, and you still will have this time-like orthogonal Killing vector field in this combination of Schwarzschild and cosmology that I'm about to describe. But if you were then try to do it with like Kerr, then you won't have that.
Yes, that's right. If it's rotating, then you won't have it. Okay, good.
Okay, yeah. So preferred reference frame might not be the thing that I'm trying to capture here, but somehow I guess there's a preferred time direction, right?
I think you say there's preferred rest spaces. Sometimes it's called preferred rest spaces.
Rest spaces. Yes. Regular rest spaces. That's what O'Neill says, right? I mean, O'Neill tries to use the word rest space to describe, I think, the foliation that comes in these FLRW models.
Of course, Schwarzschild isn't globally static either. That's another issue.
Right. Yeah.
Yeah, but we're just talking about the exterior part. Yeah. Okay. Cool. Okay, so FLRW solutions do a good job describing the observed large-scale structure, the isotropy of the universe, but obviously, very obviously, our universe is not isotropic on small scales, right? We have things like planets, we have things like stars and galaxies. And so I think maybe, again, failure might be a strong word here, but this is a limitation of the FLRW solutions, right? And so we really want to find a way to get, I want a space-time that can capture both of them. Okay, so now let's talk about combining Schwarzschild and cosmology. So recall, so what do I have here? I forget even what I have. So the Schwarzschild solution is asymptotically Minkowski, and hence this is a limitation to, and again, preferred reference frame is not the right word, but maybe I should say preferred time direction. Again, this isn't quite right because of what Shai said earlier, because the static foliation does have a preferred time direction, but really what I'm thinking of is like if you go far away from if you go far away from a star or a galaxy, your time direction really is more or less part of the cosmic flow that one has as describing the universe. So the FLRW solutions can be equipped with this, again, preferred time direction, but cannot describe the local anisotropy of the solar system. And so the goal is to find such a model of the universe which maintains the successes of the Schwarzschild and FLRW solutions, but removing these limitations. And so some history, this was really done very early on. So I think McVittie, I think that's how you pronounce his name. So McVittie found such a model all the way back in 1933. He used coordinates that corresponded to the isotropic coordinates that one has with Schwarzschild. And so it wasn't, there was some debate over what is the physics of going on in McVittie's model. Nandra, Lasenby, and Hobson, they clarified his model in 2012, saying that what McVittie found was actually something that should describe Schwarzschild and cosmology. And they derived it using spherically symmetric coordinates using tetrads. And so it's the way Nandra, Lasenby, and Hobson described it that I want to discuss. Okay, but again, this is a picture from the Hubble Space Telescope showing the distribution of galaxies. I mean, I think this picture does a good job at recognizing the homogeneity or isotropy of the universe, but still seeing the local anisotropies of each individual galaxy. Right? And so this is something that we're trying to capture, getting that local anisotropy while still having a global, something that should limit in a case to global isotropy. Okay, so we will follow the approach by Nandra, Lasenby, and Hobson. And again, we're going to slowly look at the k=0 case. That's just because it's easier. You can still do this for k = +1 and k = -1. Okay, so this is the metric for a k = 0 FLRW model. So recognize that this guy right here, this is just the Euclidean metric, right? And so I'm writing that in terms of spherical coordinates, where I'm writing these spherical coordinates, the r there in r tilde. And so their idea was to, instead of using this r tilde coordinate, which can be called like a co-moving radial coordinate, the idea was to introduce a new coordinate r, which can do a better job at describing the spherical symmetry that probably occurs in the k = 0 FLRW model, right? I mean, spherical symmetry exists in all FLRW models because O3 is a subgroup of every single one of those isometry groups. But the point is that if you introduce this r coordinate, this r here, which is equal to a of t times r tilde, then one should recognize that in the metric here you have something like a squared of t r tilde squared d omega squared, right? This is that term right there. This just becomes r squared d omega squared, right? So when you want to calculate the metric in these coordinates, then this is what you'll find. This is just a simple calculus exercise, right? You write out what dr tilde is in terms of dt and dr, and then this is the metric that you find. So this guy right here. And again, notice we have r squared d omega squared, right? And so here, this is why we're saying that r really represents a spherical coordinate or r really represents a spherical coordinate in these coordinates. H here is a prime divided by a, which is just the Hubble parameter. And again, this is just a simple calculation. Okay. So here is the Schwarzschild metric and the k equals 0 FLRW metric. And so then now let me just say what the metric that McVittie model had, but in the coordinates used by Nandra, Lasenby, and Hobson, it looks like this down here, right? This is, I'm using their initials G, M, and LH to describe this metric. And you have, one should see very quickly that you get these limitations that we want. That is that when for large R or for M equals 0, you get back the FLRW spacetime. So I'm looking at this one right here, right? If you took R to be very large, right, then this term, that term dies, and this, these all become 1, and so you get back precisely this metric here. And then if you set h of t to be 0, if h of t, if a prime is not really changing very much, right, as you're not really taking into account the expansion of the universe, then this metric really becomes like the Schwarzschild metric, right? If h goes to 0, this term dies, that term dies, and then you get back Schwarzschild. Okay. Okay. So McVittie's model, so it solves the Einstein equations with a perfect fluid. This was all in the paper by Lasenby, Hobson, but I put too many n's in that, but whatever. There should just be, there should only one n. So it solves the Einstein equations, and it does so with a perfect fluid, but they didn't actually say what the rho and the p and the u are of their perfect fluid. It's not too hard to actually find what it is. And what you find is that it really is, you get back exactly the FLRW model, again, when you take the limit as r goes to infinity or m is equal to 0. In that case, so u is again our floor velocity. You have to have this extra partial r term here. This happens even in the FLRW model, because again, in this case, these coordinates, partial t isn't hypersurface orthogonal, right? Because you have this dr dt term. So this is why you need this extra partial r term to account for that. But so then this u velocity, this u vector field is the vector field that's orthogonal to the t equals constant hypersurfaces. And then rho and p here. So this rho and p, again, these are the exact same things that follow from the Einstein equations for the FLRW spacetime. Again, if you set m equal to 0 or r equal to infinity, that term will just go to 0, right? And then you get back exactly the Friedman equations. Okay. Okay, so they studied this solution, but they who are these guys? Lasenby, Hobson. They looked at it, but they looked at it only for very specific rhos and p's. Like they wanted to consider just matter or something. But again, just like with FLRW, you can leave rho and p undetermined, right? In this expression, once you fix rho and p, then that will fix h through the Einstein equations. So we can consider different values of rho and p that one wants. And so this will be important when we start looking at geodesics and horizons. So in the Schwarzschild spacetime, partial t is a killing field, and this greatly simplifies the geodesic equations. I mean, without this fact, the geodesic equations would almost be impossible to solve. But you aren't going to have this for this metric here, right? Because unfortunately, this metric has both r and t dependence. And so, now the geodesic equations really become a system of coupled ordinary differential equations in T and R, and I don't know how to solve coupled ordinary differential equations, right? So, I mean, this is a challenge. But what we did was we did actually find one particularly interesting solution. So one interesting solution can be found when h is a constant. And so this corresponds to the case when rho and p are described by a cosmological constant. And so we can see that actually. So before I do that, let's just go back over here and let's compare rho and p. If h was a constant, then h prime would be 0. So that term dies, and then you're left with rho equals negative p, which is precisely the equation of state for a cosmological constant, right? So if h prime equals 0, that implies that rho equals negative p, which is the equation of state for a cosmological constant. So in the case where h is a constant, maybe in this case, it's not too surprising that you can solve the geodesic equations because the metric doesn't necessarily depend on t anymore. In either case, we were actually able to find one solution to the geodesic equation, which is it corresponds to the photon sphere. So the following curve, gamma of s, which is t of s located at r equals 3m and theta equals pi over 2, and phi of s, where t and phi are just given by, they're just linear functions in s. So this is just a linear function in s, and t again is a linear function in s, and L represents the angular momentum of this geodesic. And so one can show that this actually does solve the geodesic equation, which shows that the photon sphere at r equals 3m should still exist in these models when h is a constant. This wasn't too hard to show, but I think an interesting question to go from here would be to show some type of convergence when h of t approaches a constant as t goes to infinity. Because I mean, I don't think people don't believe that everything will be perfectly described by a cosmological constant right now, where there's still radiation and matter in the universe. But you can ask the question, well, what the matter and radiation will dilute and go to 0 at infinity. So h of t you can make the mathematical assumption that h of t should approach a constant as t goes to infinity. I think that this would be a little bit more physical, right? And then you can take a look at these geodesics and see if in what sense do the limit of these geodesics approach the solution that you have here. And I think that would be an interesting question to investigate. Okay, and so finally, I want to look at horizons. So these guys, when they looked at this spacetime, they were really looking at matter models, and so they concluded that r equals 2m is not a coordinate singularity in this case because they weren't able to find other coordinates. So let me back up for a second first. Actually, we know that r equals 2m is a coordinate singularity in the Schwarzschild model. This metric here is describing the exterior Schwarzschild also, but also in a cosmological universe, right? And so then the question is well, what happens at r equals 2m? Do you still have a degeneracy or not? And so what Lasenby and Hobson found was that they found that they were not able to extend it. I don't think that they proved it. They just said they can't find coordinates that actually allow you to extend. But what Anna and I were able to show is that we actually were able to prove that you can extend through this r equals 2m horizon. And so the proof, we haven't quite written it all down yet, but the idea is if you assume that the Hubble expansion does approach a constant, so you assume that the Hubble expansion does approach a constant as time goes to infinity. And again, what this means is if rho and p are really dominated by a cosmological constant as time goes to infinity, then r equals 2m is in fact a coordinate singularity. You can find coordinates that allow you to go through this singularity and go into another spacetime, at least in a C0 extendable way. And so I think that this is interesting because we do actually believe, at late time, rho and p should be dominated by a cosmological constant. Okay, and then lastly, what I have here is that the null expansion. So we calculated the null expansions for the constant r spheres in the constant t hypersurfaces, and so they are given by this formula here. I can't really see it because the screen sharing button is blocking it, but one should note that it actually is, it does reproduce what one sees in Schwarzschild when you set h equal to 0. Right? When you set h equal to 0, then r equals 2m should correspond to a MOTS, right? A marginally outer trap surface. But here we're not getting that. Right here, it depends on what h is. So the event horizon that you would get here, it does not correspond to a MOTS in this model. Okay, and I think That's it. So Outlook, there are some questions that we want to get. In particular, we really want to get a uniqueness result. We want to say something that says, like, as time goes, we want to say that their metric that they have here should be unique under some assumptions. Those assumptions will probably be something about the spherical symmetry, the asymptotic nature being FLRW, and then probably either some conditions on Ricci or the scalar curvature. I would like it to be just conditions on the scalar curvature, but I think we can prove it for Ricci, and then the proof for scalar would either be impossible or hard. I'm not sure. I really don't know. And then the idea would be to look at the k equals plus or minus 1 solution. So all of our work so far has just been done on the k equals 0 solutions. But again, you can ask these questions for what happens when you have k equals plus or minus 1. You can play the same game here, but finding specifically what the actual these functions, they're much harder. These functions that you get out, they're much more difficult in the k equals plus or minus 1 case. And then, of course, you can ask, well, what about other space-time? What about other black hole models, right? There's Rice and Nordstrom, there's Kerr. You can also ask about questions like, maybe you want to just consider a matter model, right? And then, match the perfect fluid, of a star to the perfect fluid that one gets out at infinity, and then see what happens there. Okay, that's it. Thank you.
Well done, Eric.
Let's thank the speaker. And let's open the floor for questions and discussion. Eric, can you comment on what is the relationship of these solutions to the so-called Schwarzschild de Sitter? And
So
you stole my question.
we did.
Sorry.
So we did actually show.
Chair's prerogative.
When h is a constant, we were able to find a coordinate transformation that brings you to the Schwarzschild de Sitter model. Yeah.
When h is a constant.
Yeah, which should make sense because, right, Schwarzschild de Sitter should somehow be should be unique under spherical symmetry and other assumptions.
I see. So it's included, in other words, in this.
Yes, it is. It is included.
And the solution and the geodesic solution you have so far found is actually for that case. Is that right?
Yeah.
Mm-hmm.
Yeah. So we first found this geodesic solution, and then we thought that was really cool. And then we realized, oh, this actually is probably just Schwarzschild de Sitter. And once we realized that, then it became less cool. But it still makes sense.
Mm-hmm. Okay, I see several hands up. So Eric, Amorim, go ahead.
Thank you, Eric, for very clear talk. I like the presentation style. I have a question, 2 questions about this G over the initials M and HL.
Okay.
This metric. I don't know if you said this or not. Is this something that they just came up with, like an interpolation between the 2 regimes artificially?
So the way they came up with it, I mean, they derived it using tetrads and spherical symmetry. I didn't fully understand their proof though. So because they had some sort of like new algebraic method that they were trying to use to solve it, and they said. And when it came to actually doing it, they didn't do it for this spacetime. They just said it's very similar to another case that holds. So yeah, they did some actual derivation. Mm-hmm.
Okay, and then the other question would be, is it always the case that whatever metric you have, if you then assume that the right-hand side of the Einstein equations is the perfect fluid team you knew, then you can find a rho and a p that satisfy this?
Sorry, I'm not sure if I understand the question. What exactly is the question?
So what you did after, or maybe before this, where finding the rho and the p for which this metric solves the Einstein equations for a perfect fluid. This would be always possible to do, like whatever metric you put in, you find a rho and a p.
Yeah, so no, this won't be possible. There's only going to be very specific metrics that allow you to actually solve the Einstein equations with a rho and a p. Mm-hmm.
Okay.
So like for the FLRW models, they do satisfy this. But then this is true for any rho and P. And once you specify what rho and P are, then you can determine what A is. So it closes the system, and the way normally one closes the system is through an equation of state. And you say rho is a function of P through something, something, something.
Okay, thank you.
Manali?
Yeah, I also really enjoyed the talk. Very clear, and it's neat to see that there is a solution like this that combines Schwarzschild and Robertson-Walker spacetimes. Have you guys written out your equations into a Hamiltonian picture out of curiosity?
No, I'm not even entirely sure how one could do that. So that would be interesting.
Yeah, I mean, so I think it should be possible to do so. And if you can, then you can also set up your model to, be like canonically quantized, and then you could study, say, a Bohmian model of dust in a universe like this, which might be kind of neat. Wardstruve has analyzed cosmological models, Bohmian models of quantum cosmology in the context of like FRW spacetimes. So he's already worked out the Hamiltonian representations of FLRW.
Interesting.
Spacetimes classically showed how you can canonically quantize that type of model and then write down guiding equations. And presumably you could do something here as well. And then you could analyze like the Bohmian trajectories near the singularity. And
that would be interesting. It'd be interesting to see. I mean, so does he do it for both? So you said he does it for FLRW. Does he do it for Schwarzschild as well?
I'm not aware if he's done it for Schwarzschild. He may have, but as far as I'm aware, he's done it for FLRW.
Okay, interesting. Yeah. I'll try to take a look and see. That's a good question.
Yeah.
Greg, go ahead.
Do you have fairly general conditions under which you have a well-defined Scri plus space, presumably space-like, although I'm not sure. Scri plus, and if so, can you then, does it then allow you to produce or define black holes in sort of the classical way in these models?
Yeah, so that's a good question. Definitely when H is positive, this corresponds to de Sitter, and so in that case, you should be able to have a Scri, like a space-like Scri plus.
Yeah,
but what I don't remember now is if these models, I think that the way, if you write out the coordinates in this way, the way that we have it here with this DRDT term, you might get the part that also, I'm not sure. I think it could be the case that these coordinates only describe things from the event horizon to the cosmological horizon. In which case, then that would be a problem, and we need to extend past the cosmological horizon. But I'm not sure, I can't remember. I think maybe we also might get past the cosmological horizon, in which case then you would see this space-like Scri. But you can also make the assumption that H of T should approach 0, right? As T goes to infinity, in which case then you expect to get a null Scri, right?
Yeah.
So I think it really depends on what the limits of what H of T is. And so I think that I think that's interesting because it corresponds to the limits of what H of T is. Like, in order to get that R equals 2m was a coordinate singularity and get an event horizon, you needed H to approach a constant, in which case you get one of these either null, time-like, or space-like Scris. So it's almost like there's a compatibility thing going on.
Thanks. Very nice talk. Thanks, Eric.
Yeah, so Eric, this coefficient of dt squared is cubic, right?
This coefficient.
So do you get then 3 horizons?
That's a good question. So I think like when it is the case of a cosmological constant, when it is like the case of a cosmological constant, then you should get 3 horizons, but one of them will occur past r equals 2m, right? And so I haven't fully explored what goes on in that region yet, or within r equals 2m. So I think there will be 3 horizons. One corresponds to r equals 2m. The other one corresponds to the cosmological horizon, which is way off, near infinity. And then the other one will be somewhere between 0 and r. And so that one would probably, correspond to another coordinate singularity, I'm guessing.
I see. So, well, but we don't know what kind of, what is the, I mean, this is so, so you have not explored, or has the sort of the extension of these spacetimes been explored inside the horizon, inside the event horizon?
So not yet. You can explore them because you see my function h kind of just stops at r equals 2m, right? And so then you have to say how do you define it afterwards? And if it's just a constant, then of course you know how to define it, right? But once you get to the horizon, then you don't know.
Oh, I see. Right. So I forgot that this h is actually h of t,
yes,
or something. Okay.
Yeah, this h is still a prime divided by a. And so you can say, how should one define as when you go past r equals 2m? And I'm not sure.
I understand. Okay. Yeah. That's right. And by the way, how you mentioned that you get these ODEs, how difficult are they?
That's a good question. I don't know. I should show you what they are. I don't actually have them with me. I think Anna has them, and she has the notebook of these notes that we have. So, but I mean, they're difficult in the sense that I don't know how to solve them. So, I mean,
so it's a system, right? They're all coupled to each other and so on.
Yeah, I mean, it's basic. I mean, you can imagine like the geodesics that you get from Schwarzschild. I don't think I even have a picture here. You can imagine the geodesics that you get from Schwarzschild that don't depend on time, right? And that kind of helps you solve the other ODE, right? And so here you don't have that, and you get this back and forth communication.
Well, I guess it's because you have conserved quantities.
Yeah, exactly.
So because you have conserved energy and things like that, right? Which you probably don't have here, right?
Yes, exactly. We don't have that because it's not static, but we still have L. This L is still the killing field associated with partial phi. Like this would be the conserved quantity and for the killing field of partial phi here.
Mm-hmm. Right. So there is one killing field. So there's one conserved quantity. So but now the question is, are there others?
Yeah.
That because they help simplify the task of solving this system.
Mm-hmm.
And I agree with Monali that writing it as a Hamiltonian system would also be helpful. I mean, this you can write as a Hamiltonian system, right? Just the geodesic equation.
Yeah, that's true.
That's sorry, go ahead, Eric. Greg, I mean.
I think Greg, that's just his hand from earlier.
Okay.
But Eric Amorim put something into the chat.
Just a quick comment. I think the cubic equation for R for the T coefficient would have a negative root, so it doesn't count. But I don't know. I was just trying to think about it.
Maybe that's true. I think because in Schwarzschild de Sitter, I think that is true. In Schwarzschild de Sitter, you only have 2 horizons, right? And so
can you go back to the coefficient?
Say again.
Can you go back to where the metric was?
Yeah.
That coefficient.
Because that term in front of dt squared is the same term. This one. That when h is a constant, when h is like lambda, right? That is what it is. That is the coefficient in front of dt squared when you have a cosmological constant. So then that would correspond to Schwarzschild de Sitter. You only have two horizons there, but it's a cubic equation. So I think you're right that one of them has to be negative. Right? It's not like what happens in Reisner-Wald-Nordström.
By the way, since you just mentioned Reisner-Wald-Nordström again, did people generalize this again to put actually a charge in? So
Yeah, that's a good. I don't know. I haven't seen any work on that.
I mean, it's very suggestive to just change the 1 minus 2m over r into the corresponding 1 minus 2m over r plus q square over r square, right?
Yeah, it does. It is. But then how does one interpret it, right? That's the question. I'm not sure.
Wow.
Look, there are so many people that produce exact solutions, right? And they just throw a coin into a machine and turn the crank, and then it and they don't know what they have done. No? So here one has at least somehow an idea that it could be the space-time of a charged object, either a black hole that is charged or naked singularity embedded in an otherwise expanding cosmos or whatever. No?
Yeah.
Why not?
Yeah, it would be interesting to see. I mean, you could just add in the term and then just say, okay, well, this is what I want to work on. I guess one should double check and make sure that you still solve the Einstein equation.
Yeah, exactly. Of course, you want to do that. No, that Einstein-Maxwell equations are satisfied here.
Yeah. So I guess that's what one needs to see. Do you still satisfy the Einstein-Maxwell equations too?
And that would, however, be quite different if you do it on a compact manifold, say with an S3 space-like section. Because then from Gauss law, you have to have a neutralizing background. No? So there's not just that you can put a charge in there. No? So that's it's always a total charge 0 then. So that would be quite curious to see what happens then.
Maybe you would have to have one on this side and then a negative one on the antipodal point.
Actually, that is already one possibility, but no, you take one charge and a uniform background. That's the usual Green's function for the corresponding Laplacian, say, when you do it in a non-relativistic setting. If you just put a charge on S3, let's say, in embedded in R4 in a thing otherwise in a Newtonian way, then the Laplacian has a Green's function that is has locally a 1 over r singularity, but then in addition there is an oppositely charged constant background that is sprinkled around S3.
I see. So it's like constant background that's making the charge be 0 total. Yeah,
it's just because if you would integrate this, right? So if you have minus Laplacian equals delta, Laplacian u equals exactly, you integrate that, but you don't have a boundary on S3, no?
Yeah.
So the right side would give you something, the left side would be integrated to 0, so that can't be. So the right side has to have a compensating term there.
I see.
But yeah, apparently there is something called Reisner-Nordström de Sitter.
Yeah, there is Reisner-Nordström de Sitter for sure. That is just adding in a cost. I mean, that's actually the thing I'm trying to do. Your analog work that you did with Abreu is with Reisner-Nordström de Sitter. You just add in a cosmological constant into the F term. So yeah, and in fact, actually, it would be a good question now that you say that, if we just put in the charge term here, like Michael was saying, and then see if you can then assume that h is a constant, and then see if you can find a coordinate transformation that takes you to Reisner-Nordström de Sitter. Yeah, interesting.
That would be a test, yeah.
Lots of new projects for you. By the way, Eric, one not very serious comment. If you put it LMNH, it's easier to remember.
LMNH. That's.
You know what that stands for?
What?
Luke Ma, no hands.
No hands. That's pretty funny.
I learned that from Louis Nirenberg. He once wrote a theorem on the board when I was a graduate student. He said theorem, and in parentheses, he wrote LMNH. And then people are like, what does that stand for? And it says, look, man, no hands.